Buenos días a todos. Mientras se sigue uniendo la gente, voy a hacer una pequeña introducción al tema para darle el marco de partida al webinar. Bueno, como decía, nuevamente buenos días a todos. Espero que todos estén todos muy bien, sanos, y las familias también. Hay que cuidarse. Los casos han aumentado, así que esperamos verlos siempre acá y que todos pasemos esto rápidamente. Bueno, nuevamente nos encontramos, ¿cierto?, en este nuevo taller del hidrógeno, como hemos venido haciéndolo y trabajando en este tema desde hace mucho tiempo. Para nosotros es muy importante poder presentar las distintas aplicaciones o sectores o partes de la cadena de valor del hidrógeno como parte del apoyo y la pavimentación de este trabajo y de esta solución que creemos que puede ser un elemento clave para la descarbonización en Chile. Nosotros, como decía, venimos trabajando desde el 2015, junto también con Corfo, el Ministerio de Energía, que es nuestra contraparte en estos proyectos, y la idea justamente es poder dar a las empresas seguridad, certeza jurídica, certeza tecnológica, etcétera, en la medida que se pueda, para que ellos finalmente ejecuten los proyectos. Bueno, como decía, la idea siempre ha sido aumentar el conocimiento, no solamente empresarial, técnico, sino que también público, en las tecnologías del hidrógeno, porque esta es una tecnología que va a llegar a distintos sectores, desde las empresas que desarrollan los proyectos, los integradores, los desarrolladores del proyecto, pero también las comunidades donde van a recibir esta cosa. Y este tema que tenemos hoy día de blending tiene que ver mucho con eso, en el fondo, a la llegada a la persona común, a la persona de la casa. Entonces hemos convocado siempre a distintos especialistas y de importantes compañías para que nos muestren su experiencia, cómo han visto el desarrollo de los distintos proyectos, cuáles son el estado tecnológico y las tendencias actuales. Si bien recuerdan, en septiembre nosotros presentamos un estudio donde se hizo una identificación de la materialidad de los sistemas de transporte de gas, de tal manera de ver cuáles son las limitaciones que tienen los sistemas actuales y poder eso extrapolarlo a las redes de gas de la matriz chilena, de tal manera de ver cuál es el potencial de uso del hidrógeno o inyección, ya sea en blending o finalmente a un futuro 100% de hidrógeno en este tipo de redes. En ese sentido hemos visto que obviamente dependiendo del tramo, ya sea en la transmisión del gas, que son los grandes gasoductos, la distribución y en el uso final, tenemos distintas limitaciones o distintos elementos que pueden limitar, ¿cierto?, la inyección. El uso final es muy importante, hay sistemas que son muy sensibles a las variaciones. También vemos que sobre un 20% de inyección en volumen en una red de gas presenta esto un problema también con la declaración normativa de lo que es el gas natural, por el tema del índice de WOE que se sale, etc. Entonces, todos esos aspectos lo hemos empezado a tratar para poder desarrollar este tipo de proyectos. Hemos visto también en la prensa que la compañía Gasvalpo implementará un proyecto de inyección en una parte de la red de distribución en la ciudad de Coquimbo, tratando de alcanzar a futuro un 20% en volumen de hidrógeno, donde también van a ser apoyados por la Universidad de La Serena para ver y testear los efectos que tiene este blending sobre los equipos, los electrodomésticos, como las cocinas, calefón, etc. Entonces, eso va a ser un aprendizaje muy interesante. Hay muchos otros proyectos que están en carpeta de poder ver la factibilidad de inyección en las redes de gas. La inyección de redes de gas nosotros la vemos como una oportunidad clave para alcanzar un gran grupo de personas, ¿ya? Y además poder en esta transición tener la reutilización de activos de cara a la descarbonización. Pero este mercado es dinámico, se están realizando variados estudios, muchos estudios y distintos programas y proyectos alrededor del mundo, especialmente en Europa. Entonces, para ver, analizar, discutir cuál es el futuro de la inyección de las redes de gas, su potencial, cuáles son los posibles costos asociados que esto puede tener, hemos contactado a dos muy importantes empresas que están trabajando de la mano con distintas compañías, asociaciones de gas, para ver la implementación de estos proyectos finalmente. Entonces, para esto estará con nosotros Albert van den Noord, Principal Consultant Hydrogen Energy System en DNV, muy importante, así como Jürgen Petersheim, Senior Manager Sustainable Service en PwC, Pricewaterhouse Company. PriceCooper, sorry. Nuevamente, entonces, ahora, para empezar, quería comentarles que la presentación será en inglés. Por favor, hagan las preguntas por medio del chat y en español. Nosotros las vamos a recopilar y las vamos a traducir de tal manera que al final, dentro de del panel de conversación que se haga al final, donde Pablo Tello será el moderador, Albert y Jürgen las puedan contestar. Así que vamos a iniciar. Voy a cambiar a inglés. Let's switch to English. Hi, Albert, how are you? Now is your turn. Please open your presentation and the floor is yours. All the questions will be at the end, okay?
That's okay. Can you see my screen okay?
Yeah, it's a little small. Can you put in full screen?
I can make it bigger. Like this?
Right.
Okay. So good morning, I guess, for you. And thank you for the opportunity to give a short presentation on the work we do as DNV on hydrogen blending. My name is Albert van der Noort. I guess you just mentioned, but I'm working as a principal consultant in our Groningen office, which is in the Netherlands, and working mainly on the role of hydrogen in the energy transition, where we do a lot of feasibility studies, but also look at the safety side. Maybe good also for this presentation in our office and also in our laboratories that we have in our location. We mainly look at the end user equipment. So what I want to do today is give a short introduction on what DNV does on hydrogen, and then give a number of examples of projects where we were involved where hydrogen blending was the subject. And that ranges from the infrastructure, but also, as mentioned, the end user equipment. A short introduction. The short introduction on DNV for those who do not know our company. Basically, we provide assurance, and we do that through our knowledge of the industry, but also on these different technologies. We were founded around 150 years ago in Norway, and starting in the maritime sector, where we did verification and certification of maritime ships mainly, then went into the oil and gas industry, moving forward also to the power industry, and nowadays we sort of cover the whole value chain of the energy system, so both electricity, the fossil fuels, but nowadays also a lot of work is done on the renewables. Could be wind or solar, but also in hydrogen and hydrogen-related energy carriers. As such, we still do certification and verification, but we also develop and co-develop together with the industry new rules and standards and recommended practices. I will come to that later when we also work on this topic for the blending of hydrogen. We do quality and assurance of new technologies and data, and we give expert advice on safety, technology risks, and efficiency and performance, for example. That's in a broad sense what we do in the energy domain within DNV. If you then focus a little bit more on the hydrogen, we think that we can cover the whole value chain for hydrogen. Hydrogen is not present on Earth, so you need to make it, and nowadays most of the hydrogen is produced from fossil fuels, mainly from natural gas, using SMR, where we work a lot on the carbon capture and storage of these processes, so that you can produce hydrogen in a sort of renewable way by storing the CO2 that is emitted during the production. But also mentioned before, with a lot of knowledge of the wind and the solar in industry, we work a lot on projects with electrolyzers nowadays, where hydrogen is produced from electricity and water, and then with renewable electricity you get green hydrogen. So that's the production side. And when we move forward to the transportation and distribution side, we work a lot on repurposing of gas infrastructures, but also on storage of hydrogen in salt caverns, for example, and shipping, of course, of hydrogen over longer distances via ships. And that could be in the form of liquid hydrogen, but also in the form of ammonia or other derivative energy carriers. And then finally, also we work on the utilization of the hydrogen. Could be in industry, could be in mobility, could be in the built environment where heating of houses, for example, with hydrogen boilers is a big topic nowadays, at least here in Europe. So as DNV, we offer a lot of services on all these aspects of the value chain. And in the department where I'm working, it's mainly consultancy services. So we do, for example, technical feasibility studies of value chains in different sorts, which cover these topics. So that's well, the overall view. And when zooming in a little bit more on the hydrogen and the blending of hydrogen, I think one of the major projects that was executed in Europe some time ago already, and was where we had a role as DNV, was the Naturally project. And in the Naturally project, a lot of R&D work has been done on what are the topics that you need to cover if you want to reuse the existing natural gas infrastructure and use that for the transportation, but also the use of blends of hydrogen with natural gas. So it was a large project with over 40 European partners in a period of over 5 years, and funded by the European Commission. And as said, what we did, besides the project management, also a lot of experiments. So it was really an R&D type of project. And from that, we got a number of learnings, and I think it's good to mention some of them. For example, if you consider blending of hydrogen in the natural gas infrastructure, in the networks, you have to deal with a number of aspects. First of all, it's about the materials of which the different components in the system are made. Focus on, for example, the transmission pipelines, which are mainly made of steel. How much hydrogen can you blend into such a system so that the materials are not influenced by the amount of hydrogen that is in the natural gas. So that's the more the integrity part of the pipeline system. Second part where we focused was on the pipeline risk. What happens if something goes wrong? And the percentages that are shown in this figure on this slide, I will come to that later. But looking at the pipeline risk, you can say that the risk is always well, the chance that something goes wrong times the consequences. And there we see that mainly on the consequence side, the effects with adding hydrogen are a little bit different than from natural gas. And as said, I will just show you in a minute some examples of that. And then the last part is when you have such an infrastructure system, you need to realize that all the gas that goes through the system, which would be the transmission system and also the connected distribution system, will in the end up in all the end user appliances. And there, the blending of hydrogen has the largest impact, I would say. And also on that topic, I will spend a few words in the next slide. So overall, you can see here what kind of percentages are mentioned in this Naturally project, and how much hydrogen you can add. And I think one of the main lessons from the Naturally project, and we see that also within the ongoing projects when blending of hydrogen is considered, is that there are no real showstoppers for introduction of hydrogen into natural gas infrastructure systems. So to focus in on these three topics, I made a number of slides. One of them is looking at the materials. So what happens if hydrogen comes in contact with steel, of which the pipeline is made? Then, and that's shown here on the top left, what happens is that the hydrogen molecule is split into its atoms, and the atoms, they move into the iron structure, the steel structure. And every time that there is a small pressure fluctuation inside the pipeline, these small molecules or atoms will get a small kick and move through the steel structure. And what happens is that the hydrogen accumulates in small cracks, where it influences the material properties, and the material becomes more brittle. And as a consequence of that, small cracks can develop in the steel, and that's something that you do not want. So what we did in this naturally project is experiments on what is the effect of embrittlement on different steel types that are used typically in natural gas infrastructures, and the results are shown on the top right. I will not go into all the details of this diagram, but basically what you see on the axis on the bottom is the stress intensity factor, delta K, which basically is the pressure fluctuations in the pipeline. And the two vertical lines are typical pressure fluctuations in, well, the delta K corresponding to typical pressure fluctuations in natural gas transmission systems. And then on the y-axis we plot the crack growth rate, so the speed with which a small crack will grow in time. And what you see plotted in this diagram are lines for the different blends of hydrogen. So the one at the bottom is with pure natural gas, and then 25% of hydrogen, 50%, 75%, and pure hydrogen. And you see that when increasing the amount of hydrogen in the blend, and the crack growth rate indeed goes up, as was expected. But I think one of the main lessons from this research was that if you keep the pressure fluctuation, so the delta K, below the lines indicated in this line, which is typically the situation in transmission pipelines, then the crack growth rate remains below the 0.01 micrometer per cycle, which is considered to be acceptable. So basically, the conclusion of this work was that in principle, you can use the pipeline, the steel pipelines that are used in the transmission system for blends of hydrogen up to even 100%. And that's also one of the main conclusions, which, for example, now in the Netherlands is used by Gasunie, our TSO, to develop their hydrogen backbone, which is supposed to transport pure hydrogen through existing pipeline systems. So that's on the material side. Then on the risk side, we executed a number of experiments also. We have a location in the UK, at a remote location where we can do large-scale testing of pipeline systems, for example, of all kinds of components. And what you see here are a number of pictures from an experiment that we did already some time ago on what happens if a pipeline system for natural gas and hydrogen is broken. So what you see here is a pipeline where over a distance of 1.5 meters, we make a hole in this pipeline. You can see it here at the bottom. Then it's covered with ground, and it's ignited, and what the result is a large fire. So what you see here is a large fire. If you look closely, you see the trees on the background. This fire is roughly 100 meters high initially. And what we did is we measured how much thermal radiation would come off such a, in this case, pure hydrogen fire. And then the conclusion was, if you scale that to the amount of energy that goes out of this pipeline, which is different for natural gas compared to hydrogen, then for pure natural gas, which is the blue line, is at the bottom, but also for mixed blends of hydrogen and natural gas. From the Naturally project, you see that the line is a little bit higher, and for pure hydrogen, it's even well, they sort of coincide with the blended version. But the conclusion here was also that fires, when a pipeline is broken, in these high pressure pipelines are leak, then fires sort of are the same as if you would have a natural gas pipeline. It is impressive, but the changes with natural gas and hydrogen are not that large. It becomes more risky if you have a buildup of hydrogen or blends of hydrogen with high percentages in natural gas in closed environments where you could have an explosion. So there the risks are higher. Then last part is looking at the end user equipment. As mentioned here, I think the end user equipment is most sensitive when you add small amounts of hydrogen. And that has to do with the burning velocity, which is influenced when you add hydrogen to natural gas. And what you see here on this picture, on the left, sorry, is a burner with pure natural gas. It's natural gas, but any natural gas will do here. And if we add 5% of hydrogen, or only 5% of hydrogen, then you see that there are a number of effects. One of them is, and that's all because of the higher burning velocity, that the flame crawls into the burner. So there is a risk of a flashback of the flame. If it goes even further in the burner, it will extinguish, and then there's a free outflow of gas, which is something that you obviously do not want. So the second effect is that when the flame comes in contact with the burner deck could overheat, so higher temperatures, and it could destroy your burner. And the third effect is that the temperature of the flame is also higher, and because of that there is more emissions from NOx. So there are three effects when adding hydrogen for combustion systems, and of course there are all kinds of combustion systems which react a little bit different, but basically these are the main effects. And the same happens if you add hydrogen in an engine, where we have the combustion in a chamber, and then an effect called knocking of the engine could take place, which would destroy the piston of your engines. So as mentioned, the burning velocities are different when adding hydrogen to natural gas, and because of that, also the use of existing equipment for end use could be very sensitive for adding hydrogen to your network. Of course, you can deal with that, and that's this is one of the researches that we do together with the industry in the Netherlands, and that's the development of a flexible burner system for indirect heating. This is one which is typically used for heating larger apartment buildings, and we have adapted this system in such a way that it is able to use natural gas 100%, but also blends from 30%, 40, 50, 60, all the way up to pure hydrogen in the last picture. And what we see is that indeed the temperatures of the flame are higher, and because of that also the NOx emissions are higher. But there are all kinds of mitigating strategies for lowering the temperature of the flame, which also would help to lower this NOx. The main conclusion here is that there are all kinds of innovative ways of solving the end user, the problems that we have with end user equipment, so that you can still use all kinds of blends of hydrogen. But the main thing, if you add hydrogen to an existing system, is to have a look on what are the existing end user appliances, how are they dealing with this blend of hydrogen. And finally, one of the last projects I want to mention is that it's called the HyReady project. And in this project, we try to collect all this knowledge which we gained from the, for example, the Naturally project, but also from other research, and convert this knowledge into practical guidelines for TSOs and DSOs when they want to implement a certain amount of hydrogen in the network. So you can see on the right, it's quite an extensive consortium from all over the world, and you'll see companies from the US, from Canada, but also from Europe. And what we do there is make the guidelines not only for the transmission and distribution system, but also for the end user equipment. We have a look at the compressor systems, and nowadays we are working on the storage systems and the underground storage of hydrogen in salt caverns, for example. So this is an ongoing initiative which is still open for new partners. And with that, I would like to end my presentation, and I hope that I give you a short overview of the work that we've been doing on hydrogen and blends.
Okay.
I guess we will have the questions after this.
Yeah. Thank you, Albert. As I said, the question and answer will be at the end, and the conversation panel now. Yeah, we have some questions, but Pablo take the question at the end. Please, Jürgen, will you launch your presentation? And the floor is yours.
Just 1 second. Let me get the presentation up and running, and then.
Okay.
Here we are. Share. There you go. It's here.
Perfect.
So let me know. Can you see my slides? Oh, my slide. It's only one. Yes. Thanks everybody. Thanks for organizing this event. And I think it's quite complementary to what my D&V colleague just said on sort of the sort of more examples and how we view the world, basically the market. So after some sort of technical specifications. Yes, Jürgen Petersheim, I'm with PwC in the Sustainability Services section of the company. So what we do is, I mean, we do a lot of consultant work around, I mean, obviously regulatory aspects of hydrogen. We look at market dynamics quite a lot. So we do techno-economic assessments for hydrogen, but also we look at, you know, what subsidy schemes are in there. How does regulation impact the uptake of hydrogen and the deployment of projects? So, and then we go all the way towards, for example, aspects of certification, but then also in terms of assurance, how everything is reflected in proper reporting schemes. Hence, so we are probably more the economic regulatory aspects to what the D&V does in terms of technical competencies. So I guess we complement as well, and I'm pretty sure in the upcoming discussion we can answer all the relevant questions. Coming to the topic, because I think we only have sort of 10 minutes and then we go into the discussion. Quick view on the hydrogen uptake. Well, there's a focus on the European market, but with a breakdown into the different applications, which I think is key to discuss blending hydrogen or not blending hydrogen. Because there is a discussion on, if you look at certain sectors, think about the housing sector for heating, that's where you would need blending, but for other applications, so think about heavy industry, for example, there is a demand of industry to have a clearly specified fuel and not necessarily a mix. So there are sort of two different pathways within this discussion. And I will talk later on a bit about, well, a few blending examples, but also on sort of how can pipeline infrastructure evolve to make sure that we transition from what we have today, sort of basically natural gas driven pipeline infrastructure, towards a sort of hydrogen pipeline infrastructure. If you look at the different sectors, there are a couple of sectors that are very important in terms of feedstock. And feedstock is basically, think about feedstock for the chemicals production going in. So ammonia is one, but also in refineries you have this. So, and this is sort of the darker red area here. And you see this is sort of existing feedstock. Well, not going to change that much. There's even in the 2050 scenario, there might be a bit of a decrease, but then you get new industry feedstocks. And with this new industry feedstock, this really mainly focuses on supplying 100% hydrogen within the pipeline infrastructure. So because these clients, companies, they need a clearly dedicated feedstock, not variations within that. Then you see that the industrial sector certainly has an influence in terms of high temperature, so as a fuel. So their blending rate would be different proposition. So certainly more flexibility in regards to blending. Then we have this heating and power for buildings. So this brighter orange section, where it could play potentially a fairly large role in 2050. Sorry. So you see it here in the business as usual, but also in the ambitious scenario. I think that's where most of the discussion really comes around blending hydrogen today, evolves around. So we have that. I have an example later on where this is being done at a substantial blending rate. And then on the transportation sector, we would again need clearly defined 100% hydrogen sort of volume flows towards transport applications. And then in power generation and buffering, a bit similar. I mean, gas turbines can take blends of hydrogen, but if we think about sort of in the future, the power generation via fuel cell technology, so there's a bit of a limitation in regards to the flexibility of methane versus pure hydrogen. That's basically sort of a nutshell on, well, what's happening in Europe and where could blending play a bigger role or not play a bigger role. What does it imply? I mean, obviously it reduces the carbon intensity of sort of energy supply, but it also leads to the fact that if we start having higher rates of hydrogen in the network, we can transport less energy. So I mean, the density of hydrogen is different. Yes, you compress it, but still there would be you cannot transport as many megajoule within the same pipeline as you can with natural gas. It certainly is a fairly sort of simple way of, or simple doesn't sound positive here, but sort of it's a non-complex way of basically bringing hydrogen into the market, because you can start with smaller fractions. You can then sort of pass the little price premium. You can distribute it over a large share of customers. But then at the end of the day, the decarbonization effect is going to be sort of limited. What we see over today is in Europe, you need to stay below 10% of hydrogen blending in natural gas grids. So that's already allowed. You can certainly sort of put up to 10% in. A few are doing it, but there are certainly some test cases. You can reach blending rates of up to 20%. You also get the sort of regulatory approval for that. Without infrastructure changes, you need to do a proper assessment of the pipeline network. So I mean, as mentioned before, you know, look at hydrogen embrittlement, look at the materials used, look at compressor valves, etc., used in the system. So then you can get this accreditation. Towards 20%. Higher blending rates are in discussion. So there are sort of some tests going on, prototype tests basically, or pilot tests, with up to 30% hydrogen blending in the natural gas grid. There's one example which I sort of want to focus on a little bit, because it was just announced, I mean, actually yesterday, I believe it was, or at least I read about it, that this project, it's an operation for a while. So it's in Saxony in Germany, so it's in the eastern part of Germany, where a consortium of 3 companies, so Avacon, DVGW, and E.ON, so utilities and gas, energy and gas utilities, basically, they've partnered together to expand the percentage of hydrogen being used in the gas infrastructure. They're blending already for quite some time up to 10% of hydrogen into the grid. So that's what's regulatorily allowed at the moment. So there are no repercussions or limitations on doing that. But now they decided to blend up to 20% of hydrogen into the grid, starting this heating period. So basically starting now, because the heating period in Germany, I mean, it's already ongoing, and they will do sort of proper testing over the entire period, basically the next 6 months, to see how much hydrogen can the system take. Are there any bottlenecks? Will any problems occur? So how does it work sort of if we start blending it properly in a larger system? It certainly is a project that's being sort of closely monitored. It's a pilot project that shows how can we transition towards this net zero economy, net zero carbon economy, I mean. Something I'm pretty sure we will get sort of more information about soon, and also sort of enhancing the public knowledge on what is actually possible and what constraints, what problems, challenges may or may not occur when actually putting it properly into systems. So I think after this heating period, we will know a bit more about this and get a better feeling of, well, where are the limitations, in addition to all the pilot testing that has already been done. So I think it's a very interesting project here. Another one, a lot smaller and not in Europe, but it's in the US. It's a high blend, so it's a 2-year research project that's ongoing. I think, I mean, we find such projects in many parts of the world. So we find these type of research applications in many European countries and elsewhere. But I just wanted to sort of mention it as for sake of completeness, really. In regards to building this or expanding the hydrogen infrastructure towards the sort of capacity requirements we need for a 2040, 2050 net zero economy. In Europe, there's this European Hydrogen Backbone project. I'm not sure if you heard about it. It's a good report. It's publicly available, and I'm happy to send the link afterwards to this. It's a cooperation of different gas and infrastructure utilities, really, and they have a look at how can a gas grid expand over time. So how can we connect as many customers as possible? And you see, it starts here, sort of. Until the 2030s, there's going to be a limited grid, sort of in the northwestern part of Europe. So basically stretching France to northern Germany, going along the Netherlands, starting to connect really first hubs of industrial consumers. So these guys, their focus really is on not blending so much, really, but repurposing pipelines towards the hydrogen economy. Because if you look at this part of the world here, it's a fairly industry heavy cluster, and they really start looking at, well, we need for our processes, we want a high share of hydrogen or 100% hydrogen in our pipelines. Then it really goes, this is going to expand over time. So you see that more and more parts of Europe will be connected. So you see the Spanish grid expanding, certainly also with some local production, because Spain has pretty good resources, but similarly here expanding to Denmark, where we could then again connect larger offshore wind parks and sort of make use of the renewable resources we have locally, even though as Europe we will not be energy independent, so we will certainly rely on energy imports. So we will import hydrogen from many parts of the world. I mean, there are discussions with South American countries, with the Middle East, but also longer discussions with Australia on importing hydrogen in the future. So, and it's basically this twofold approach. While this really looks more at sort of supplying 100% hydrogen to the industrial consumers, where we expect significant demand, then there are these sort of pilot prototype plants where hydrogen is being produced, in a distributed manner. So basically in a certain region, let's say Saxony, for example, where they then start putting this hydrogen into the natural gas grid, mainly for the purpose of decarbonizing the part of the heating and building sector. And then if you look at the European perspective a bit more, you see this Highway 27 project. So it's certainly a project where there was the idea on where to start first with the repurposing of these pipelines. So try to connect industrial clusters first. And there was the analysis of sort of what is the cost of kilometer investment for repurposing versus new construction. So and you see it's almost a factor of 4. So if you start repurposing pipeline infrastructure for the user, for the transport of hydrogen, it's significantly lower cost than the construction of new pipeline infrastructure. And then from a European perspective, you see where are sort of potential demand centers first. So you see that from Rotterdam, you can supply some of the industrial clusters here, so with almost 10 petajoule, and then 5 petajoule going to other industrial clusters. While you see that some smaller applications, you would have not such a high demand. So you would say there is the potential to either repurpose smaller pipelines or then have this blending approach to provide the necessary energy towards these different clusters. Additionally, I mean, if you talk about hydrogen and putting into pipelines infrastructure and then the end user, you have to think about storage. So storage is something where we see some activities, not many. I mean, there are pilot projects going on. One very interesting one is actually this one here in Bad Lauchstädt. It's a salt cavern where they want to pilot the storage of hydrogen in the salt caverns. They see the concept of putting a 30 megawatt electrolyzer onto the site, and then really see what are the effects of storing hydrogen in the system. Does it work? Is there any sort of sort of gas creep towards the existing salt caverns? Does it have any effect on the salt cavern, any effect of the existing equipment? So storage being sort of, I feel at least understood in the entire hydrogen value chain, but some projects, there's another one in Austria going on, I believe, is an aspect we see more and more, and I'm pretty sure, I mean, if you want to develop the hydrogen economy in your different territories, then you will have to look at the storage option as well. And I think these technical learnings then from other parts of the world will certainly help and can be transferable. Basically concluding quickly, because we want to have a sort of a good discussion. I mean, hydrogen will certainly, including blending, will be relevant in the future, because it is a low complexity way of introducing hydrogen into networks. It's an option to pass on the cost premium to a broad set of consumers. Hence, you don't have to pass it on to a single consumer that gets sort of a significant hit in energy costs. You can share it quite nicely. What we see, obviously, there's investments in infrastructure are already on its way, but we really need to see this infrastructure being expanded for pure hydrogen pipelines, but also being expanded in terms of, if you want to transport larger shares of hydrogen, we need to have a look at the infrastructure and accredit it that we can sort of give larger parts of the gas grid available to plus 10, 20, 30% of hydrogen transport within these existing pipelines and all the associated equipment with it. With that, I would conclude, and I'm looking forward to the discussion round we are going to have now.
Okay, thank you, Jürgen. Very interesting. Please, Pablo and Albert, could you turn on the camera? And also, just a comment, and as I said, or I comment in my introduction, the possibility to inject hydrogen into the gas pipelines or the gas infrastructure depends of the most sensitive equipment, or to the capacity to change different elements into the grid. For example, variables or coolers or measures in order to know what is the quality of the gas is passing into the gas grid. And I see the different question about the use the hydrogen, for example, in distribution part, not only in the transmission part, etc. And that will be very interesting to hear from you about this consideration you have, that we have to inject the hydrogen, or in the future 100% of hydrogen. Please, Pablo, you take the role now.
Yeah, thank you, Rodrigo. Thank you, Albert, and thank you, Jürgen. It was a really interesting presentation, both of them. And now we have a lot of questions, but I want to take my place as my role as a moderator. I want to know about, from your side, your years of experience. Maybe, how do you see the future? It's very simple, but it's very complicated question. Maybe we can start with Jürgen. How do you see the future of the blending? And when I ask this, I am thinking, if you see that the new infrastructure will be only hydrogen, or we have to see like parallel hydrogen natural gas infrastructure, or whatever, in terms of infrastructure, how do you see the next investments and the move?
Yeah, I think, I mean, in terms of infrastructure, oh, I'm muted actually. No, I'm not.
No, you're not.
It says I'm muted, so well, doesn't matter. So as long as you can hear me. I think in terms of significant infrastructure spending, I'm pretty sure we will see in dedicated hydrogen pipelines. So where you say, well, we'll start supplying hydrogen to large industrial consumers. Think about the steel, think about the cement and chemicals industry. So nonetheless, I think the blending is going to play a relevant role, and it will expand because at the moment, I mean, if the repurposing of the hydrogen infrastructure takes place, it's going to be a long process, right? And you've seen it from this European Hydrogen Backbone report. Not all of Europe is going to be covered by a sort of a proper hydrogen infrastructure soon, and that means we will need some local production of hydrogen, production, where we might not always have a client who's capable of taking all the additional cost premium. So, and that's why I think it's when we have certain sites, local hydrogen production sites, or later moving into hydrogen production hubs, they will be close to industrial centers where they start satisfying the demand of the industry. But additional hydrogen, because we need to start moving in all sectors. We cannot just say we start moving in one sector, and that means we will see this hydrogen also being used in or blended into the national gas grid to then start decarbonizing all the applications that sit at the end of this gas grid. So, sort of in short, I think the large part of the investment will go into repurposing or potentially build new builds, but to not only focus on one sector, but and start decarbonizing the entire economy as we need it to reach a Paris Agreement, we will see more and more blending to rates of certainly +10, +20%. To start decarbonizing the residential sector, the housing sector, commercial buildings, etc. So that's my view, at least.
From your side, Albert, what do you think?
Yeah.
I think you have a very more like in the testing applications, the real possibilities. What do you think about that?
No, I agree with Jürgen, but if you look at infrastructure systems, always to connect the supply and the demand of an energy carrier. And in this case, if we consider hydrogen, and especially green hydrogen, we also have to consider that making green hydrogen is quite expensive. So the premium value of hydrogen is probably more valued in specific industries than, for example, the heating sector. So if you could use the hydrogen for feedstock for producing ammonia, for example, directly, probably more a better business case than blend it into a small percentage in the natural gas grid and use it for heating houses, for example. That's one. And the other thing is the availability of infrastructure. As Jürgen showed, the backbone in the Netherlands is intended to be pure hydrogen. And that is because we have the luxury that there are multiple pipelines next to each other that transport now natural gas from the large gas fields to the centers where most of the gas is used. And some of them will be available and others are not. And I've also seen projects, for example, in Canada or in the US, where a single transmission pipeline is considered, where you want to go into blending hydrogen, which means that the entire system needs to be adapted. So there's a difference in what is the availability of the infrastructure, and where is the value of the at this moment well, rare hydrogen most valued.
Okay, thank you. We have one question very related to this, and it's for Jürgen, but I think you can both have comment about that. Is which kind of materials are being considered right now for new gas pipelines in Europe? If you have some inputs about that, because yeah, it's related to the new infrastructure or how the new investment are going to be set. Jürgen?
I think, Albert, you have a better position to answer than I am.
As far as I know, the conventional steel types are still used also for the hydrogen pipelines. So it's not much different for the new gas pipelines.
I think most.
One of the things that we researched in the Energético project, if you have the higher grade steel materials, they are in general less suitable for transporting hydrogen than the lower grade steel.
I guess the main cost driver really comes from different compressor equipment, different valve equipment, so not necessarily from the steel. So,
in terms of
just adding quickly, I mean, we have the luxury that we know material as well. I mean, not I personally, but for example, think about the chemical sector, the petrochemical sectors. They are dealing with hydrogen for decades and decades and decades of pure hydrogen applications. So it's not that we don't have the knowledge. We do have the knowledge. We just have to transfer it to the different sectors and to the new applications and so upskill other parts of the economy. So that's relevant. But in principle, the expertise and safety codes to deal with hydrogen, it's all available, right? So it's nothing we have to invent.
Yeah, you're very right. Yes.
There are quite extensive pure hydrogen pipeline systems already out there, even with higher pressures than we used for natural gas. The big question is when repurposing existing pipelines, whether these materials are also suitable, and the condition of the pipeline is suitable for converting to blends of hydrogen.
In terms of the quantitative risk assessment applied to hydrogen pipelines, where are the critical points and which solution have you deployed to manage the risk until a large level? That is a question maybe for Jürgen. It was directed to Jürgen.
It was to me, okay. But I guess the parts of the pipeline material itself is sort of well understood. The critical points really are sort of what compressor equipment to use, what valves to use, and then sort of have sort of the proper safety mechanisms in place to, what safety mechanisms in place to mitigate the risk. But in terms of critical points, I would say certainly, I mean, of the welding aspect of it, but critical points really are sort of valves, compressors in these projects. Albert, maybe you want to complement.
Yeah, I think when looking at the QRA models themselves, you can say that the chance of something going wrong is sort of the same as for natural gas. It doesn't matter if somebody cuts a hole in a pipeline, what kind of gas is going through the pipeline, so that's the same. The consequences can be different, and what I showed is that if the consequence is a fire, then the consequences are sort of comparable or even less for hydrogen compared to natural gas. When the gas is built up in closed environments, and especially at higher blends, up to above 20% or above 50%, then explosion is different. The combustion speed of such a mixture is much higher than for natural gas. So there is on the technical side. On the regulatory side, you know a bit more about that, but at least in the Netherlands, the pipeline systems for natural gas are within a different set of external safety procedures than pipeline systems for other gases, on which hydrogen is one of them. So for the other gases, they are considered to be more dangerous. The rules are much more stricter. So if you would convert the natural gas system, then you also need to change at least the way you look into external safety requirements for the government.
Similar in Germany, right? In Germany, you have similar. You know, we have rules for natural gas, and then for the for other gases. So similar to the Netherlands. I mean, at the end of the day, it's European legislation. And it's more stringent as well. So, but more stringent, but we know where the stringency is, so we know what to address. That's the benefit.
And here we have two questions related to maybe to the same point. One is related to the odorant. If you have any idea what is happening to the odorant when you inject more the hydrogen, if it changes properties, or does it affect a lot or not?
I can comment on that. The odorant is mainly for the distribution grids, so the high pressure grids do not use an odorant, at least not in the Netherlands, probably also not in Germany. So it's at the lower pressure grids, and there's an ongoing discussion what kind of odorant should you use. And the main challenge there is that most of the odorants that we use nowadays contain sulfur. And if you add sulfur and you use the hydrogen, it's mainly considering pure hydrogen, by the way, but if you use that in fuel cells, then it can become a problem. If we use the hydrogen for boilers or combustion equipment, then the odorant itself is not really an issue. And we are, at least in the Netherlands, considering the same odorants for hydrogen as for natural gas, because the public is known to the smell of a dangerous gas in this case.
Also, here is a question, and I'm pretty sure you have already worked on that. Is related to the how does the hydrogen injection affect the polyethylene pipelines? We know that it's more possible or more feasible to inject there. And related to the project that Rodrigo mentioned, we have a new project here in upcoming in January, hopefully, injecting 5%, starting with 5%, and they want to reach 20% of the hydrogen in a polyethylene pipeline of 5 years ago, more or less. So, what do you think are the main topics related to that injection? Where we have to be like put the eyes on, Albert?
Yeah, so if you consider polymer materials, then the question is whether the hydrogen permeates through the material to the outside of the pipeline. That's obviously something that you do not want. There have been experiments on the amount of hydrogen that goes through such a pipeline, which is very limited. So at least here, it is not considered to be a real risk that the hydrogen permeates through the pipelines. Even more, you see in, for example, the UK, that most of the distribution grid, well, parts of the distribution grid still contain cast iron, which is for the transportation of hydrogen, not preferably. So they replace the existing grids with polyethylene pipelines for that. And they are ready for the transportation of pure hydrogen. So you see in the distribution grids, a lot of these steel materials are replaced by polyethylene or other polymers.
And related to this, also in the more in the distribution, we have dealing also with the quality of the blending of the energy, so the WOB index. In Chile, our regulation asks us or to the gas to complain a limit of a quantity of WOB index. And how are you managing that kind of issues, more normative issues in blending in Europe? How is your what do you know about that?
Jürgen?
Jürgen? You're muted. You're muted.
I need to step out for 2 minutes because my son, his school, his teachers are sick and they sent me to the office, so I have to pick him up on the elevator now. And I'll be back in 2 minutes, and then I'm happy to answer. I'm really sorry about that. I did not know this is sort of a bit of a chaotic day. I'll be back in 2 minutes. Hey, sorry. If you have another question, Albert, maybe you can comment on something else in between. Back in a sec.
Well, Pablo, I can say something about the WOB index. If you add hydrogen to natural gas, then the WOB index goes down. So typically you have a band in which the WOB index should be. And we also use this band to determine how much hydrogen you could add to your system. Because if you know what is the upper and the lower limit and you know how much it decreases, you should have, preferably have a higher WOB index of your gas, so that you can add more hydrogen before you cross the lower limit. That sort of determines how much of the existing infrastructure or end user appliances at least can also be suited for the blends of the hydrogen.
And yes, but my question, yeah, we do have also this range. But how are you dealing? Do you know how the European Commission or the normatives in Europe are dealing with in order to, because when with this range you have a limit. For instance, in Chile is almost up to 20, or we can. It depends on some calculations, but after that you cannot inject more blend because of the normative. How is the discussion right now related to that in order to reach more percentage of hydrogen injection?
I mean, at the moment it's allowed until these 10%. It's not a problem. The 20% is something we see this pilot project, as I mentioned earlier. The other thing is if the regulation, if we want to go to more than these 20%, which I mean at large scale I do not see it within the next few years, because I mean if we reach 20% within the entire system, so then that's certainly a significant amount of hydrogen that we would have to produce, and we don't yet. So but I mean, in terms of regulation, I'm pretty sure we will see, and I guess the DNV and others are involved in that, sort of in adapting the technical standards, understanding where the critical bottlenecks, and then making sure that technical standards are reflected, particularly investigating what is current infrastructure availability. And what we will then see, I mean, we will see sort of specific technical assessments for certain parts of the gas grid to understand, well, yes, we can go higher, or we can't go higher, or we can go higher by replacing the following things, right? So I think there will be a sort of site-specific, region-specific assessment of the grid to make sure that technical standards are met and there are no safety regulations. So not no safety regulation, no safety aspects. Safety regulation.
I have another question related also maybe more in the technical way regarding the mechanical integrity of the pipelines with the blending, of course. What mechanisms, measures, or mechanisms associated with the damage mechanism illustrated at the beginning of your presentation are you using or are you seeing in the market as a solution? This is for Jürgen, because I think you in the starting point of your presentation you have some slides with a picture.
Yes, exactly. I mean, it's yeah, kids me yeah, so you caught me off guard. Yes, I mean, in terms of yeah, just one second. Yeah. This has not happened to me yet, so it's a first. Let me tell you.
It's pandemic times. It's no problem.
You know, you go one day to the office, and then the teacher starts to strike. So yeah, well, it doesn't matter.
Yeah, I can repeat.
Otherwise,
no problem.
I'm thrown off guard.
No problem. Is which kind of mechanism or measures are you using in the for the blending and associated with the damage mechanism illustrated at the beginning of your presentation? I think in your presentation you start with some slide of a picture of that.
So which measures are taken to start blending hydrogen, basically? I mean,
yeah, for the security aspects, yes.
I mean, the first aspect is certainly is a proper technical. I mean, up to this 10%, you can just blend it in, right? And then that's it. So because it's allowed from a regulatory perspective. If you go higher, you do these sort of technical assessments for the part of the gas grid, and that means you have a special technical consultant coming in, understanding, well, where are potential bottlenecks, and the potential bottlenecks are known. You know, we mentioned the compressor, we mentioned valves, we mentioned expansion kit, and obviously at the end of the day, the end of pipe applications. So, and these measures are taken. So you do a proper technical assessment of where are the risks along the pipeline, taking in the hydrogen, transporting and distributing it towards the end application. And each of these steps, so the transport, the high pressure grid, the low pressure grid, the applications, they will be assessed by a technical expert, and only then it's allowed to increase the percentage above these 10%. So the measure basically is a proper technical assessment.
Related to that, I think Albert has been involved in some of this technical assessment, or I'm right on. What can you tell us about the process?
That's a good one. Yeah, it's just what you just explained. So we assessed what kind of materials are used in the pipelines, what would be the effect of the hydrogen blends on these materials, also on the compressors. They are quite sensitive, as mentioned, on blends of hydrogen, and for the end user equipment as well. And there we maybe can spend a bit more words on that. There we make a distinction between the types of end user equipment that you have. And so when looking at combustion of hydrogen, you could distinguish, for example, between fully premixed burner systems or partially premixed burner systems, or non-premixed burner systems, which all have to do with the amount of fuel, which is then the gas with the hydrogen, together with the air or the oxygen that is used for the combustion, of course. And all those different technologies of burner systems, they react differently on blends of hydrogen. I could say that the partially premixed systems, and which are mainly used in the older equipment, they are most sensitive. Again, and then of course you have the engines and the turbines, and for that they are typically very tuned for a specific gas quality for an optimal operation. So if you have larger turbines or larger engines, we often need to go to the vendors or the manufacturers of this equipment to see whether this specific model is suited for certain blends of hydrogen.
Just related to what you mentioned, related to the gas turbines or very big equipment, and there's a question: if you can explain the adaptive devices to be used in the blending gas power energy, if you have special devices for the adaptation of the blending for this, this equipment.
Yeah, so the example that I showed with this blue device, and that's a large burner system, not very large, but a larger burner system. So what we typically do there is we measure what kind of composition the flue gas, so the gas going out of the burner has. Based on that, tune the flow of the gas and the air in this specific burner system. So we are not changing the burner itself. It is the same as for natural gas, but we tune the control mechanism that directs how much air is put into the burner. And with that, we're just changing the so to say the operation system of the burner. You can already accommodate quite a high percentage of hydrogen.
Related, this is either. Do you know if there are any commercially available technologies to unblend natural gas from hydrogen? Yeah, I think that is a very, very structural question, because and it's related to the first question I did, is if you see there will be only dedicated hydrogen, or is more possible to have like unblended devices. How do you see that, Jürgen? We will have like new devices for unblended the feedstock?
I somehow doubt it, to be honest. So because I mean, if you need pure hydrogen, you will, at larger quantities, you will aim for a sort of a pure hydrogen pipeline. Because if you think about the green hydrogen production, you know, there are so many losses in between, from electricity to hydrogen to transport to potential liquefaction, ship it somewhere else, and then you start blending in the grid and you try to unblend. I cannot see it, to be honest, so I doubt it. I'm pretty sure there are some membrane processes under development where you could do that. But I don't really see it as a growing market. What is in discussion and what is being developed at the moment is the aspect of sort of not changing the gas infrastructure at all, leaving natural gas in there, bring the natural gas to a certain site, and then use something like methane pyrolysis, so split the methane into the carbon and the hydrogen, and then use that on site. So there are systems doing that, but that is not part of the whole blending process, just a different type of hydrogen.
And Albert, do you know if there are some devices to unblend? They are more like in the technology.
Yeah, as Jörg mentioned, there are membrane processes there where you can extract hydrogen from a blend. We once also had the question whether you could totally separate the blend from the hydrogen, and that becomes quite difficult because you have large quantities of the gas, and in order to do so you would need enormous installations. When now producing natural hydrogen from natural gas, after the SMR, also the hydrogen is purified, mostly done by pressure swing absorption, PSAs. Those kinds of technologies would also use if you at the end of the pipeline would need to separate the hydrogen from the natural gas, and that's quite well, I can't really see why you would do that, just as Jörg just mentioned. But there are some indeed membrane systems that allow you to extract well, rather pure hydrogen from a blend of natural gas and hydrogen, smaller amounts.
I have just before we finish, I have one I missed, and it's related to the engine generators. Which kind or what are the safety parameters for the use of hydrogen with natural gas for combustion equipment that are designed from the beginning to operate with H2 in the mix? I mean, when you start we did an assessment right now, and this I can share that. We can share it's all already available in our webpage. But it's related to if you have a genset and you want to put hydrogen in the combustion in the internal combustion engine. So which kind of trouble you can expect in that case? Do you know anything about that, Albert?
So for engines, you mean?
Yes, internal combustion engine.
Yeah. So the main problem there is what is called knocking, and it's an uncontrolled combustion inside the cylinder, which well sort of destroys your engine. So that's something that you really do not want.
What do you mean? And you put that one picture in your slide, I think. Yeah.
For hydrogen combustion in internal combustion engines, yes, this knocking is very important. Is an aspect you have to consider. But in engine, actually, the adaptation to hydrogen as a fuel is possible in sort of quite a lot of applications. So I mean, we see some suppliers already offering converting existing natural gas-fired engines to hydrogen as pilot cases. So in principle, the equipment is reusable to a large percentage, but you have to look at the combustion specifics of the particular application. But in principle, it's sort of simpler to use and adapt hydrogen use in a gas engine compared to gas turbine, for example.
I think we are coming to the end, so we will have Rodrigo, have you seen? I have one question. Have you seen what is doing Anglo-Belgian Corporation and JCB with motors? So we engines or marine engines and machinery, so heavy-duty machinery. Jürgen or Albert?
The use of hydrogen in this machinery?
Yes, have you seen that? Because we had a webinar like I think 6 months ago or more from Anglo-Belgian Corporation, which was in a joint venture I think with CMB Tech from Belgium, okay. And they were doing or creating some kind of internal combustion engine with hydrogen and also GCB in heavy duty machinery. They announced something the last week, I think, or they have been announcing something. No.
I think it's in Scandinavia or the UK. There is actually there's a ferry or a fishing vessel was converted to the dual use of marine diesel and hydrogen. So there are some applications in the blend in sort of heavy machinery. I'm not aware of many applications. So what we see on the OEM side, sort of from the supplier side, that they then start designing these transport or heavy duty applications for the pure use of hydrogen. Except if you think about gas turbines, for example, in gas turbines it's pretty common to talk about blends of hydrogen. So.
Again, here we have a very good one related to the what is the average compression increase requiring pipelines when blending up to 20? That is, I think that is somehow critical because it depends on the segment where you're injecting, I think. What do you think, Albert, about that?
So what was the question? The
amount of if you have to increase the compression when you inject more hydrogen.
Yeah, so we've done some calculations on the compressors, and it shows that if you add a little bit of hydrogen already to the gas, that the existing compressor, if it is an existing compressor for natural gas, is very sensitive. So you are in the head curves, as they are called, you are quite easily at the top. So it means that you, and I'm not quite sure what percentages they are, but quite easily need to replace your compressor. And then you can, of course, design just as we did for the engines or for the combustion system. You can design new compressors that are capable of increasing the pressure for certain amounts in such a blended system. But the question here is whether you can use the existing ones.
Yes. And to finalize, I will ask you, starting with Jürgen, maybe, which are the next steps for PricewaterhouseCoopers in terms of hydrogen blending, and also what would you recommend in the case for the Chilean case that we are starting with these blending initiatives, but there's a lot to do. We have a lot of homework here. So, which would be your recommendations or for the next steps?
I mean, from what we see here in terms of hydrogen blending with our customers, it's pretty much only the housing residential customers that approach us towards hydrogen blending, right? Most of the others, the industrial clients, the transport clients, they approach us and to talk about sort of pure hydrogen supply towards the applications. So for the residential sector, it's a bit different. That's at least what we see. What I would recommend, I mean, for the Chilean case, I would certainly argue that you have to start with some demonstration projects, right? I mean, there are lessons learned from Europe, so try to get in touch with these companies. I'm pretty sure there is potential to talk, to discuss, share some information within a confidential framework, I would say. But I would try to leverage as much information as possible and then start applying some of these learnings to small dedicated local projects where you say, well, this is where we have the best renewable resource to produce hydrogen at least cost, and then choose these dedicated parts of the network to start testing a share of 10%, 20%, and see if the learnings we have made here, if they are replicable to your part of the world, and ideally try to get anything out of existing projects where you can say, well, these were challenges for us, so that you can address them early on. And I'm pretty sure there's a willingness to cooperate.
From your side, Albert, you have been working a lot in this cooperation and coordination of projects in between a lot of different stakeholders. What can you say? Comment?
Yeah, I totally agree with Jürgen. There's many knowledge out there which could, well, be used to assess whether the network is suitable and in general, but again, the learning is also in doing it, and then you should start with smaller pilot projects. We've done that in the Netherlands. You see them in different countries as well. Another aspect which is important, I guess, is also to be prepared for the future. So start in an early phase discussing with the regulators or the legislation in order to make sure that the equipment that is put on the market already now is all suited for example, blends of hydrogen, so that you are not installing new equipment at this moment, which in a couple of years' time, when you are a bit further in the process, needs to be replaced once again. And of course, we are happy to support in this.
Okay, I guess we are coming to the end. I would like, of course, to thank you very, very much for your time. And maybe Rodrigo want to make some final words to the presentation. But from my side, thank you, Jürgen and Albert, for taking this time and to complement this webinar in an excellent way.
Well, thanks for giving us a chance, I would say, and sorry again for the disturbance here.
No problem, Jürgen. We are a lot. Yeah, thank you very much again, and both, because that was quite interesting, and we have many challenges in order to advance in this development. So thank you very much. Thank you for your time, and we are in contact. Other question: the presentation will be available in order to publish, or if you want to modify in order to make public that the public, also the attendance, and are asking about if they can have the presentation. It's possible.
Yeah, I'll send you a version.
Thank you very much. Okay, I switch to Spanish again. Muchas gracias a todos los presentes. Muy interesante las preguntas. Nosotros, como digo, estamos recibiendo toda clase de inquietudes, preguntas, empresas que estén interesadas en estos temas, como GIZ, y como también un participante desde la parte de financiamiento de Alemania, o los nuevos financiamientos alemanes. Estamos atentos a que las empresas nos hagan llegar sus inquietudes respecto a este y otros temas para poder ayudar de tal manera que puedan postular las empresas alemanas involucradas en estos proyectos a líneas de financiamiento. Así que ya sea en tema de blending, ya sea en tema de transporte, etcétera, por favor, quedamos abiertos para eso. Así que cualquier pregunta respecto a este webinar y a todo lo que hemos tenido y todos los proyectos, nosotros estamos encantados de recibirlo. Así que muchas gracias a todos y que tengan buena semana. Chao, chao. Bye, bye.
Gracias a ti. Hasta luego.